things that we have to do for our API chapter very quickly, which is our, we were supposed to be doing this annually. I think it's been a while since we've done this. Election of our officers. They're elected annually at this May meeting. We have to have a vote of the majority of the members present and vote to elect officers again. We have a nominating committee, which is our executive board, and they present the board at this May meeting and the names of all the candidates for the offices to be filled. Now, we can have nominations from the floor, and we would greatly appreciate that. If anybody would like to spend a little time working on our board, we would certainly appreciate it. So the who we have is Bill Boykin. He's our membership chairman. We have Sammy Graham, who's here. Sammy is a past president and did programs for years. I see him back there smiling. R.L. Hilben is our treasurer right there. Matt Hill is our special projects chairman. Aaron Hope, I don't think he's here today. He's our website guy. I am a chairman of this, Rick Knapp. Cliff McCon is a past president. Phil Owens is a past president, the special events. Alan Fortmiller, where are you? Alan's, there he is. Alan is our scholarship chairman. Kathy Roar is a past president, and she's the secretary of the organization. Jeremiah Smith is a program co-chair also. Randall Thompson, he is my co-chairman here as president, and he does special projects. John Ungerich is our arrangements chairman, and Gordon Zimmerman is our scholarship and golf chairman. So, do we have any nominations from the floor? That's easy. Can I have a vote by hands to elect these officers for the 2021-2022 year? Aye? Aye. That's more than a majority. Thank you guys very much. Okay. Now, we can get to the good part of the meeting, which is Travis Gray, Vice President with Basin Engineering back here. I'll tell you a little bit about him. Everything's on the phone these days. Travis is Vice President of Basin Engineering. He's a degree petroleum engineer, and he's worked in key operations, engineering and planning and development positions for Range Resources, Ascent Resources, and Basin Engineering. As VP of Basin and its contract operating entity, Basin Operating Services, Travis holds critical roles in the management of production and facility operations in Oklahoma, Texas, and New Mexico. Since joining Basin in 2016, Travis has been providing value-oriented production strategies and facility designs to clients that help maximize uptime and minimal costs. So please help me welcome Travis.
Okay, so before we get going, I just want to take a quick moment. I just really want to thank everybody for coming out. If we just take a moment to kind of reflect on where we were a year ago, right? You know, fist fighting over toilet paper and, you know, cooped up in the house with my wife, you know. I mean, like I said, there's a lot of things that we really have to be thankful for. And the fact that we're starting to see this industry turn around, we're starting to see kind of rig counts come up, we're starting to see activity. That's a real blessing, right? So I just want to say thank you for everybody coming out. I kind of forgot what faces look like. So, you know, it's really nice just to kind of see a whole bunch of faces and, you know, kind of start to see ourselves turn out at some unprecedented events, right? So with that, does anybody want me to wear a mask? Or?
Mine.
Okay, all right, just making sure. All right. So today I'm going to present on a topic that's pretty close to me. Like, I'm real fascinated by just kind of flow behavior, flow pattern effects in wellbores. And it's been something that I kind of carried through, started seeing a lot of this come up, horizontal well drilling, ESPs, downhole pumps, things of that nature, and spent some time, Tulsa University has a real great artificial lift consortium called Tulsa University Horizontal Well Artificial Lifts Project. They do a lot of flow loop research that you can kind of see, and I think one of the notes about our job, right, is that we talk about engineering, talk about civil engineers, they build a bridge, right? You can see it, right? You can measure every aspect of it, right? Same thing with mechanical engineers. You have an engine, right? You can understand every aspect of that. Petroleum engineering is difficult. We're 3 miles beneath the earth. We never really truly get to see or truly appreciate what we're doing. We always have some indication, right? Maybe it's not full comprehensive understanding like we'd always want to. So a lot of literature, a lot of time spent just in my mind really trying to visualize what we see down hole, and ultimately how does that translate to surface, okay? So with that, just in general as an observation of kind of our industry and what I see discipline-wise kind of coming in and out of organizations, right, is that typically we like to think of the whole kind of technical discipline as this cycle between reservoir drilling, completions facilities, and production, right? And existing in every one of these silos, everybody's got a job, right? Everybody's got some metric that they're being held to, right? So I mean, pick your yardstick, right? And we're always kind of thinking about, hey, this is how I'm going to get measured, this is how I'm going to get weighed, in a given day. And my point here, and timely enough, I went on ahead and I just threw a target in here because we're obviously the H&H shooting sport. We really got to bring all this together. It's not one thing that really makes a good well. It's not the facilities, it's not the completion, it's not the reservoirs, the production. I can easily, have a completed cost per lateral foot, make that target, right? And then, okay, well, what happened, right? Why are the results not there? So it's really, really important that we understand kind of a job versus the job. The job is we've all got to work together, truly, in a team. Kind of have to get out of our mindset, and it's really important to understand, right? Okay, well, even though I may not be the drilling engineer, what drives success for the drilling engineer? What drives success for a completions engineer, right? And how do we all really come together to drive goals, right? So, with all these things, one time or another, we're probably all getting judged or weighed by it. And of course, up in the corner, I just threw this new guy that's coming into the industry called ESG. All right, so he's here to take your job. So, what does this ultimately look like? Teams who engage and communicate across all disciplines to complete the job versus a job drive great results. All right. How many people in the room have a production curve that might look something like what's on the left here? Let's say presentation over, go home, we're good. You guys already got it. So, here on the left, we've got a well, it's underperforming. Give this to the reservoir guy, this is hard to fit. What are the results here? What's the driver? Is it the completion? Is it how the well was drilled? Is it something on the production? What's wrong? Right? On the right, pretty clean. Right? And you can fit this, you can kind of understand it, the results in the area. And these two wells are in the same area. They're about as next door regionally as you could probably hope for to kind of get an offset comparison. Right? So what's the drivers here? Why are we underperforming on one well? Why do we outperform on another well in the regional area? So I'm going to discuss one aspect of maybe why. There could be others, but just from an observation, having been involved with kind of the design of the surface and production facilities, I'll talk a little bit about that today. So quickly, background information. Right? We talk about flow patterns, talk about regimes, okay? I already know everybody's already kind of been through this, but just kind of a quick refresher, right? Increasing gas rate as you kick wells off. You got to work through your regimes before you can really get to a critical velocity or an entrainment rate really that just kind of allows you to have good clean flow, right? So bubble flow, slug, annular flow, and then eventually an annular mist flow, right? A lot of wells in Oklahoma are on gas lift. A lot of wells are trying to get above critical rate. Once we kind of see that, things get a little bit easier as far as how we process handle fluids on the surface. Similarly, decreasing gas rate. Eventually, right, your well's dead. Okay. So, kind of taking that, understanding our flow regimes, talk about wellbore geometry and what we call flow patterns, right? So a flow pattern would be something like here at 90 degrees, when you've got gravity working equally on two different density fluids, okay? So you have your gas, which is less dense, and you have your water, which is obviously more dense. or really this is kerosene in this particular flow loop animation, but you have stratified flows at 90, okay, everything's kind of moving at an equal velocity. When you start to tilt things really subtly, there's a lot of changes. So at 92 degrees, we call this downflow, right? And just, just kind of putting some rough numbers on it, you might have 20% of your pipe is being occupied by gas. Okay, well, why? Coming downhill with it, it doesn't necessarily want, it's buoyant, right? It's kind of floating, right? So it doesn't move at the same velocity that gravity will affect the water as it's kind of come down in the pipe, and that will therefore kind of thin. So as the faster that it moves in the pipe, the thinner that column really is. So now you've got kind of fluids that are slipping across each other, right? And that rolls all the way downhill. And similarly, you've got an upflow situation, right? So you kind of come up the curve in a lateral. Now you've got 80% of your pipe. Gravity's kind of working differently on our fluid streams in our wellbore. And so you'll have about 80% maybe hold up, not 20% of your pipe. We've actually used this to kind of design where we position intakes for pumps, right? Because we want to keep them shrouded in liquid. We want to have a good natural gas separation. So a lot of this is really mindful, things to think about, things to visualize and understand. Then things start to get more complicated, right? What happens, right? And all this water rolls down the hill and kind of hits the heel. A real interesting part, there's a lot that happens at the heel of the horizontal line when they're going toe up. And I get what I kind of call this hold up slug flow phenomenon here in this particular deal. So if you can imagine all this water kind of rolling downhill to the heel, right? It then gets this resistance and immediately kind of recoils, right? It starts to push back into the pipe. Well, all this gas is kind of moving slower, okay? Builds up pressure, right? Well, it builds up enough pressure, it surges, right? Pushes it around the heel, kind of evacuates it. And this is all just relative to the geometry. There's no really getting around this, right? This happens in the wellbore, and you're going to get these periods where you're going to have more gas, more liquid, more gas, more liquid. And there's really not a whole lot you can really do about it because the densities of the fluid are different, obviously, between gas and water. Come up to 45 degrees, you get some real strange things. I call this kind of reverse and backflow, where you can actually see that with these slugs coming up, you'll have intermittent periods where you just have this fallback of fluid in your wellbore that will then get caught by the preceding slug and kind of evacuate it out. Throw a third phase in here, it gets even more complicated. I've seen a lot of this on surface where we'll run pipelines, and we'll kind of do the algebra on this, and we'll say, okay, well, we think the friction and pressure drop is going to be X across the mile. All right. Turns out that there's a lot more friction in the pipelines. Well, we have gas, right? That's kind of just little miscible gas that's kind of in the water breaking out into the pipelines. We've got undulations. It's almost like a lateral at surface. But if you were to go hot tap that pipeline kind of on a high, you would see some really strange surging and flow effects. We've actually observed this. So we get glimpses of this at surface, but again, without really, putting a lot of time or kind of effort into research into this, I just don't think it's something that's completely understood yet. One thing that I would really like to see is like a velocity profile that comes with a directional plan maybe, right? And how all this works, in a lateral. And, that's some stuff, some future research maybe that might come forward, and whether or not, there's any benefit to really how we account for these velocities in our horizontal wellbores. So then, all right, how does this work? Right? Obviously, it's happening in the completion design. Okay? I've got this slug flow, I've got this surges, I've got this geometry that's just going to be conducive to it, I've got different density fluids, and what does it look like? We get rock. Right? We see some real hammering effects. And people are drilling longer and longer laterals, right? Wells are getting bigger and bigger fracs. Things are getting more and more strong. The violence of what we see at surface as a result of these patterns is just continuing to increase as we continue to make better and better wells. So these are wells absolutely in Permian. Some of these videos are a little difficult. I'll play them again, to kind of fully appreciate, what we're seeing. But I mean, we're moving, right? And you can almost see the slugs hitting our first stage separation, right? As we try to kind of deal with what I ultimately kind of refer to as just the general violence of the flow pattern. So what happens? Well, eventually, like anything, you take a paper clip and you bend it enough and you work it enough, it breaks, right? All right, everything's got its yield. So we're actually now starting to see effects. Wells get so strong that we've got facilities that are starting to kind of tear themselves apart. Right here, we don't do this anymore. We don't thread anymore. Everything I do is flange now. Right? We used to kind of have some temporary facilities, things that we would throw them in for multiple reasons, one of them being emissions. This doesn't happen anymore. Right? So we just got to think about this. We got to think about, I don't want to have a release, especially today, right? ES&G, okay? And so it's really important that we think about these things, right? We understand, okay, how do we incorporate these designs to the facility? All right, so a case study. Real simple, our flow path here is complicated. You find something like this, real common, kind of throughout Oklahoma. There's a couple different styles people talk about, kind of Newfield style, kind of continental style, where you might see with continental, you kind of got 30 by 10s, right? Then it goes into kind of a low pressure 75, kind of vertical heat retriever separator. You might see kind of what we call really more of a Newfield style. Invented now. We've got horizontal heated three-phase units. We still have some front-end separation, maybe two 30 by 10s. I try to minimize the amount of equipment that I have, because each stage of separation or each piece of equipment that I have, in that system, I've got to hold pressure on, I've got a dump tube, right? It's more piping, it's more 90s, it's more, and just inherently being a production engineer, I'm very mindful of that, right? I want to have the lowest pressure, I want to be able to achieve the lowest pressure facility that I can, right? Because ultimately what that translates to, that low flowing wellhead pressure, is a kind of a radius of investigation, right? A drainage area, that's going to be the biggest. It just gives me the best shot. Whether or not it's truly meaningful or not, I don't know. I just know my job, right? That's part of this whole kind of big equation here, is to make sure that I don't have a whole bunch of restriction at surface, right? So it's real critical, because when you think about gas lift, gas lift is probably the closest thing to a natural flowing well, right? What kills natural flowing wells? High wellhead pressure, right? So you want to get the most out of your system. You gotta have to be mindful, and you want to try to design for at least achieving, right, the lowest pressure possible at surface. Ideally, I want to ride line pressure, right? Because that's it, right? That's the wall, right? Whatever I've got to sell into, if I can ride line pressure throughout the system, that's great. I've done everything I can to try to make the well the best I can. So real quick, wellhead. Generally, we'll just kind of have wellhead show up. We run a lot of 4-inch flow lines. You'll have here in this particular setup right here, it's a 30 by 10, 250 pound two-phase separator. It's kind of the front end unit. 72 by 15 heated three-phase is what we call it, where you kind of get some flash gas off. The majority of the gas obviously peeled off 30 by 10. Then you've got the 72 by 15, and then you've got kind of your oil and your water going. So not a complicated setup here. We then do have gas lift system kind of coming back into the well. So it's testimonial. Took this directly from my operator. Says, hey, explain to me what's going on in this facility, right? That I kind of showed you guys the production deal for. He said, wellhead pressures would drop, and there was not enough available buyback gas to keep compressors from going down. Within 20 minutes of the compressor going down, the wells would die. After kicking off the compressors, there was always 2 kicks. The first one was a really stout kick, up to 500 psi, and then the second was 50% of the first. It would be a straight fluid surge, and it would knock the compressor down on the high suction. It would take 2 to 3 hours before we would get the first kick. We would have to wait for the first kick and manually pinch a 4-inch overt valve on the separator to keep the compressor from going down, on a safety valve from shutting the well in on high separator pressure. We had to use overt valve because there was no choke at the well. It had been removed because they didn't want the restriction there. Okay? So, you look at a facility like this, it looks good. All right, I mean, it's kind of on face value, it looks like it's built well. Everything's sized correctly, for the forecast. Why doesn't it do the job? All right, why are the operators really struggling with this facility? Okay. So, the job. Being a production engineer, I'm not a facilities engineer by trade. Okay, so my education, kind of where I come from philosophically, is more grounded, probably in a notable sense. Okay, so like I said, I tell people this all the time. So we optimize the completion design to accommodate reservoir deliverability while limiting any restrictions at the surface. Right? It takes an army, it takes the tribe. Okay, I can't just do the facility. Right? We've got to do all these parts really well together, and we've all got to really help each other do all of this together to make a great well. So, problems I've kind of picked out here, right, based off what my field operator has imparted to me. First thing is that everything is sized correctly. All right? I mean, there was nothing wrong with the handoff of the type curve or the forecast to the facilities engineer. He took the numbers and he designed everything correctly. right? The problem is, right, is that it doesn't account for that instantaneous rate. Right, what happens? It doesn't account for flow pattern. All right, so if you were to pull a SCADA plot, instead of type curve forecast for offset wells, you would see these surges, right? 3 to 4 million a day, maybe, right? Maybe 6 million a day. Right, then you would see kind of things drop off, and you just get into these patterns where you have a really hard time, kind of just lining out. Now, in aggregate, cumulatively for the day, okay, yeah, we made the forecast, right? But you got to kind of dig deeper, and you got to get a little bit more granular with, okay, well, what's actual behavior anticipated to be? I over-design and I oversize everywhere. Why? I don't trust the forecast. We're given information to say, hey, size for this, and I oversize just knowing, right, that the directional plan or however we're going to drill this well is probably going to yield me some flow effects that if I just do it by the book, I've got no relief, right? I've got no give, no grace, right, kind of with the facility. So, efficiency-wise, I probably get a pretty low grade, right? But in being able to maintain uptime in a facility, okay, and prevent compressions from going down, prevent unnecessary ESDs, that's what I'm really shooting for, okay? Because ultimately that's going to give the reservoir engineer the best picture of the curve that he needs to fit. Things are going to be clean, wells are going to be up. I don't have operators running off the location. That's going to help minimize my costs, and that's just what we kind of think about. So again, a lot of the times I say, hey, this is what I recommend. I hope people don't ask me a whole bunch of questions about what can this facility really do. Because it's definitely oversized, probably for the application when I do it. So the instantaneous rates is something I always ask people. I said, hey, okay, well, what's your well going to do? So it's going to do this. Okay, what's the instantaneous rate going to be? We have that conversation about that, and that kind of helps things a lot when we're doing the design process. So the problem two, first stage separator has less slug surge capacity in the same MAOP as the second stage separator. There's no relief. There's no give, right? So you hit it, right, you take a straight fluid surge, incompressible fluid surge mainly. It's going to drive that pressure up really quick. All right, we've got nothing to really dissipate it, and we're locked out. All right, well, it's going to go down maybe on a high pressure ESD. Problem three, we don't have enough available gas in the line. And this is a big problem with this facility. I'm showing you something really bad, but we've got 3 compressors. There's a component of this where you really have to have a conversation with somebody if you're going to do multi-well pad, and you may have pressure on a line, but it doesn't necessarily mean that you've got volume, okay? So that's something that needs to get addressed. Poor compressor performance for field service, right? It's not always about bottom dollar. I hate breaks, you guys, but sometimes when you pay just a little bit more, you're paying for a little bit better quality mechanic, you're paying for a little bit better call out, okay? And you kind of be mindful of that, right? Because they're a part of the team too. No flow control to wellhead. I have a choke, right? At least the guys know they're going to get a big kick once they get this thing kicked off. They've got to wait 3 hours. If they could go out here, set the choke at the wellhead at about a ½ inch, they could drive away, which hit, come back in the morning, they can open the choke back up, it'd probably be okay, right? So flow control is good, right? And that's what they're using that orbit valve for, right? They have to wait, and they're going to pinch it in. So flow control is great, but it's kind of counterintuitive to what we want the well to do, right? Now we're trying to hold the well back. We are restricting it. We're pushing back, right? So you got to, if you can imagine it, you've got a wave on a beach, you've got a boulder that's rolling in, it's hitting a wall, falling back, right? Ideally, I just want that wave, got to hit that beach and roll up, and roll back nice and smooth. That's what it's going to do. So I really want to receive the well. I want to catch it as best as I can without trying to really motivate it at surface, because I personally believe that, really kind of trying to disturb flow a whole bunch is probably counterintuitive to what we really want to do from a flow assurance side of things. Problem 6, tight spacing of the facility creates need for additional fittings, 90s that contribute to additional restriction at surface. One of the things that you kind of see here, there is a lot of 90s here, where we have a tight footprint, we're having to make things fit, right? Everybody knows, right, that's just going to add additional restriction. I mean, look at a flowback setup, right? When you turn out a flowback and you just go to your choke, how much pressure do you lose? We have to balance the choke over, right, in order to maintain within 10 PSI. So that every 90, every piece of pipe, every fitting that you put in is another point of friction. So longer runs, fluid runs, right? More oversized valves, things like that. Really kind of help absorb the violence, right, from the well. All right, so solutions. Oversized first stage separator. The lines and valves to accommodate higher than normal instantaneous rates due to slug insertion. As just kind of a general philosophy, like this particular facility has 2-inch dumps, 2-inch flow lines. Most of the facilities that you'll see that I build have 3-inch dumps, 3-inch flow lines, oversized. Well, why? Okay, well when I look at that dump valve designed with the specific gravity of water in mind, right? Heavier water, least water, right? When you first bring a well online that's real fresh, it doesn't have a weight. It's not, I have a changing conditions even with the densities and the weights of my fluid as I just kind of even go through the flow process. Just real early when I have a really high rate, I'm not going to get the anticipated performance that I would normally expect, right? So we hedge our bets a little bit and we just kind of oversize a little bit. The cost of that upsize was really nominal. The cost of a call out pretty much covers that, right? If I have to send a guy out at $100 an hour. So, solution 2, first stage separator is 2 times the amount of the second stage separator. Right, so I take that fluid surge, I'll have 500 to 600 pounds maybe, right, at the wellhead. That'll hit that first stage separator. I might get a surge in pressure, which if you look at that first stage separator, that's a big giant white spot in the line. It takes a lot of energy out of the flow line, okay, and it just absorbs it, right, so you can dissipate it. Here, you have a 250-pound unit, 250 pounds is the wall. There's no way to really take that energy and kind of dissipate it, dampen it throughout the facility, right? So, I mean, on these facilities, I generally just run with about a 300-pound conventional back pressure valve, and it'll go out at 300 pounds. I have a 500-pound separator, all right? One of the advantages to kind of stripping out gas first is I can get 90% of my gas sold, right? And I can turn out, well, venting's a bad word today. I can briefly, right, vent or go to flare or whatever I need to do, and I can still sell 90% of my gas. The gas is a lot of the issue when you're talking about flow patterns and flow effects. So we just have a little bit higher pressure unit, and that's got benefits too. You know, at least I can sell 90% of my gas and keep moving oil and liquids and keep going about my business. Solution 3, buyback gas needs to be thoroughly vetted with the gas purchaser, especially when multiple units are fed off a common line. You know, I wouldn't take you know, people's word for it, have a model for it. We really understand the issue. And you make sure that you got an available, you know, 1,500 MCF a day, 2,000 a day in that line. And not only that purchaser and that system is going to be able to tell you what they can backfeed you, what you're going to need to do, but you know, when you're talking about really scaling up and doing a lot of gas lift on the pad, those volumes start to jump quite a bit. Solution 5, in absence of, solution 4. Compression service provider needs to be thoroughly vetted with special consideration of quality and field service mechanic. I believe in my people. I believe in my field operators, right? And, you know, we have names of good mechanics, right? And we kind of listen and says, oh, wait, you know, where's he at? What's he doing? You know, that means a lot to me. You know, because again, shut-in economics, downtime, and wells, if I can just maintain up, I mean, all those little small things add up. Solution 5, in the absence of available surge slug capacity first stage separator, adjustable wellhead choke needs to be made available to field operators. We should not be using orbit valves to control wells, right? Choke is the appropriate way to do that, right? You can do it, but I can tell you one thing, they're having to open up that, they're having to close that valve a little bit more and a little bit more and a little bit more every time they go out there to deal with this thing, all right? So you're headed toward a maintenance issue, okay? I need to prevent a release. And then solution 6, avoid tight spacing in constructing service facilities, minimize 90s. I understand real estate is very important, all right? I'm happy to build post frac. I'll stay out of your way, okay? Just think about it. Don't give me like a little small box, right? I would rather, you know, design, if you kind of set for me my dimensions, I had to live with that. But understand what I need and why I need it. You know, let's have a conversation about why I may want a little bit more space and you know, what that might do to kind of help the well, help the performance. So this is the unit that we'll typically see out in the field. This is kind of our first stage separator, and we just designed this in-house. I mean, this is kind of what we came up with for what we thought was a reasonable solution to kind of a lot of the flow kind of surge issues that we see. This is technically a 3-phase separator. It is not a 3-phase separator, okay? It's a 2-phase separator. The 3rd phase would technically be sand. Because a vertical separator, you can dump sand a lot more effectively off of than a horizontal separator. where you'll get a lot of caking and a lot of buildup on the sides, and you got to put a flush line in it, do all these things. So that's kind of the downside of horizontal units, is that they're not as easy to kind of flush and clean out. This vertical separator is big. It has 4 times the settling volume of 30 by 10. It's 48 by 15. Really, I got 4 times the volume here. So when I do a 5-minute retention time on this, for what we're moving in this particular unit, I can accommodate flow. I mean, if it's 4,000, 5,000 barrels a day, not a problem on flowback rates early time, right? It's designed with that in mind. So I'm almost getting, you could say, you know, I'm paying twice as much to build this unit, okay? But if I use 2 30 by 10s, I've only got 1 stage of separation, all right? It's almost 4 times the separator of a 30 by 10. And it really helps give me a capacity to kind of really absorb, you know, what I don't know is gonna happen. What I can't control how the well's gonna get drilled. I, in large part, can't control how the well's gonna get fracked. I affectionately refer to this unit as the trash can. Okay, and it's a little bit of a jab because, you know, it's all the trash that drilling and completions gives me in the field. But, you know, what it basically is a unit that just helps quiet the well, helps receive the well, right? It's you know, way oversized. It could do, you know, 12 probably to 15 million in gas if it was actually like a true unit. But it's just a good, big, wide spot in the line where I can also kind of minimize my flowback costs a little bit, because if I run with this problem of just kind of light sand, right, this kind of really annoying, do I need to get flowback off here? I can set a quarter pit off the bottom of this. I can kind of walk back, dump sand once, twice a day. It's real efficient for that. I can keep it out of the heater. I can keep from developing hot spots, having to do more maintenance, having to do clean outs. It's just a little bit more efficient. It is not a sand separator, but a lot of times we'll walk away from wells, no sand, right? Maybe 1 or 2 stages haven't been contributing yet. All of a sudden one day, guy goes out there, throws the dump, Jim and Eddie Christmas. You need to get some flowback equipment out here. It gives me enough grace to kind of just, you know, respond, right? Without filling up a heater full of sand or anything like that. This unit's not made to be permanent. One of my favorite words that I love, right? It's kind of capital redeployment, right? I like moving stuff. If it doesn't need to be here, get it off, right? Let's go take it to another well. So I'm not buying one of these for every well. Eventually, when it no longer serves its purpose, we move it. We move it, we put it somewhere else, plug it in, right? You know, we move things around, right? Those big 3-phase heater treaters, they don't need to be there. Eventually, a 30 by 10 maybe, right? When the well calms down, we don't have as many of the flow effects and things are moving a little bit slower. A 30 by 10, 4 by 20 or 6 by 20, 75-pound heater works great, right? A lot of that equipment laying around, a lot of it easy to find. But, you know, we can take $50,000 unit, $25,000 unit, and we can reuse that, right? So stay dynamic with your programs. You know, we're a big component of modular design, right? Let's just kind of look at our equipment and, you know, where do we need to move, what do we need to do? So, one of the unique things about working at Basin is that I can really quantify the economic impact of this because I had an invoice for every call out that we went, you know, to try to help deal with this. A particular operator for that well had a 2-hour minute, basically. They had a 2-hour time that they expected their wells to be back up when they went down. So they wanted their wells up within 2 hours. So we had a call-out structure, we built it, we said, okay, hey, you know, we need to be wherever we need to be, we'll be ready to go, we'll have to go back up in 2 hours. The result of a lot of what we observed on this was a 900% increase, right, in cumulative call-out dollars versus the offset well from another operator or their previous designs. So, I mean, you know, it's kind of one of the, almost looks like a funny number, but it's true. I had 64 call-outs over the same period of time versus kind of 6, you know, to 7 call-outs for the other facilities. All right, they just maintain up. So, conclusions. Not to be Captain Obvious, but if operators can't achieve desired results, healthy B&C activity is not sustainable, right? I want the reservoir engineer to layer me in a great forecast, right? As much as I can help him early time to justify drilling more wells, I need to do that. If there's a lot of questions, right? If there's a lot of things we're working on, we're slowing down progress. Conclusion 2, design operator friendly facilities and field personnel, thank you for it. All right, don't make things really complicated. These guys got to hit 30, 50 wells a day. My ideal scenario, when the well goes down, operator shows up to the pad, hits the compressor, goes home. Doesn't have to worry, right? He gets to spend more time with his family, right? He doesn't necessarily want to do call outs. He doesn't like having to get up at 10, 2 o'clock in the morning to kind of have to respond. So, helping those guys out and having that structure will not only minimize your cost, but it kind of helps, the wear and tear that you might have on a guy when he's having to come out every couple of days to address a new high profile well. It's just not really being very agreeable. Conclusion 3. It's a lot easier to turn down a facility than it is to turn up a facility. Turn up's hard, right? If I've got to upsize a separator, if I've got to upsize a flow line, if I've got to upsize a meter run, yeah, I can build in some redundancy, but it's hard to catch it on the top side, right? I can always turn it down. I don't have to run volume into a facility. I can run 10 barrels into this thing. It's not going to be the bottom way oversized. That's going to be the criticism I go out there. Well, I got all this fixed up, right? But when I'm trying to catch the outperformance scenario, right, or I'm trying to account for flow effects, it's hard, So sometimes maybe spending a little bit more money, not be so tight, not be so efficient, isn't a bad thing, right? Because you'll get forgiveness, and in the field, you need that sometimes. Conclusion 4, slugging and surging aren't going anywhere. I'm probably going to have a really, really hard time convincing everybody not to drill 12 wells. Right? It's not going to happen, right? So we got to live with that. We got to think about that, right? These flow effects aren't inherent, again, to the geometry of the wellbore. Conclusion 5, just really work as a team, right? Don't just talk about it. Everybody's, we've got the buzzwords and what we do, but understand what really drives success for each team member's individual responsibilities so that the job can get done, right? When you look at the facility, when you look at flow pattern stuff, kind of understand as much as you can across disciplines, how do we help each other, right? Because we want to hit the target, right? We want a great well. And it just takes a lot of cooperation, it takes a lot of understanding. So don't get too caught up in your silo and just kind of what your individual responsibilities are. If you can't make great wells as a team, well, the team's not going to be around, right? So, questions?
Travis, who builds your separators?
Big Iron Oil Field. We have about 60% right now of their shop capacity. And they're out of Elmore City. We do have a couple other fabricators we work with, but mainly a lot of our engineering and stuff has recently been with them.
What's one of those 48 by 15 cost?
25 grand.
Easy group, huh?
Hey, again, guys, thank you so much. Again, this is a real pleasure for us to come out here. Where we were a year ago again, I can't even begin to thank you so much for coming out and just being able to interact with people again. It's a real blessing. So thank you very much.
Thanks so much, Travis.